Welcome back to the deep dive. This is where we tear through dense, really critical technical documentation. We skip the tedious parts and we try to extract that concentrated knowledge you need to be, immediately well-informed.
Right. And if you're looking for those strategic shortcuts, those key aha moments, you are definitely in the right place.
Today, we are embarking on a deep dive into the absolute bedrock of software quality engineering.
We are. Our source material is really the gold standard, the ISTQB Certified Tester Foundation level syllabus, specifically the V4.0.1 update. And this isn't just like a guide for passing an exam.
No, not at all.
It's the universal language. It's the definitive map for every professional who's aiming to build reliable software.
And we're talking about everyone. We mean developers who need to write robust component tests, project managers who are trying to scope quality, BAs defining requirements, and of course, the dedicated quality engineers. Our mission today is foundational. We are going to examine how professional testing goes way beyond that old idea of just finding bugs at the end.
Right.
We want to understand how quality activities must integrate into and really drive the entire software development lifecycle, the SDLC.
That's the core of it. We're establishing the common ground that defines quality control, no matter what your stack is, what industry you're in, or your specific methodology.
And that underlying shift is it's paramount, isn't it?
Oh, absolutely. The syllabus sends a really clear signal here. Modern software creation is defined by rapid change, and testing has to adapt to the development approach you choose, whether that's a rigid, sequential approach, an iterative model, or the continuous flow of DevOps.
So for you, the learner, this knowledge is about moving from just basic fault detection to, strategic quality engineering.
Exactly.
Okay, let's unpack this. Before we can even talk about lifecycle integration, we need a shared vocabulary. So we're starting with Chapter 1 and the most basic question. What officially is testing?
It's a great place to start because the official definition is broader than most people think. Testing is formally defined as a comprehensive set of activities. It's not just one thing. It's not just execution.
A set of activities, okay.
And these activities are designed for two primary goals. First, to discover defects. That's the detection side, the one everyone knows. And second, to evaluate the quality of software work products.
And when you say work products, you mean everything?
Everything, from the very first requirements document all the way to the final deployed code.
And central to that evaluation are these two terms that everyone, and I mean everyone, mixes up. Verification and validation. Let's clean that up right now.
Yes, let's. This distinction is so critical because it dictates who should be testing and what their focus should be. So verification. Verification is the process of checking whether the system meets the specified requirements.
The spec.
The spec. The question you're asking here is, are we building the product right? You're checking it against the design documents, the requirement spec, the architecture. It's really an internal check of correctness.
Okay, so if the requirements doc says the system has to process 1,000 transactions per second, and I run a performance test that hits 1,000 TPS, that's verification. I'm verifying the build against the blueprint.
Precisely. Now, validation is the mirror image. It's checking whether the system meets the users' and stakeholders' needs in its intended operational environment.
So the real world.
The real world. The question now is, are we building the right product? You might successfully verify that the system meets all 1,000 requirements, but if the user interface is so confusing that no one can actually use it to do their job, the system completely fails validation.
I see. So you can build the product perfectly right, but it can still be the perfectly wrong product.
That's it in a nutshell. Validation ensures the final output delivers actual business value and satisfies the intended user. You have to have both.
Okay, so verification is a technical check against the documents. Validation is a business check against reality. This immediately tells me that test objectives have to be much broader than just finding bugs.
They are. They're diverse and they're strategic. I mean, beyond just finding defects and causing failures, testing has to evaluate all work products, not just the code. We're testing the requirements for ambiguity, the design for potential flaws.
You're also, I assume, reducing risk.
Hugely. You significantly reduce the overall risk of future inadequate software quality. Testing builds confidence in stakeholders, in regulators, in users that the system will work as they expect. And increasingly, it's about ensuring compliance. Meeting those contractual, legal, or regulatory standards is a formal test objective now.
Which ultimately informs the decision to release.
It's one of the main inputs for that gonna-go decision.
Okay, let's nail down another critical distinction that often causes a lot of confusion inside development teams: testing versus debugging.
Yes, they are fundamentally different professional skill sets, and they happen sequentially. Testing is detection, debugging is repair.
Detection versus repair, I like that.
So testing detects or exposes defects. If we're running the software that's dynamic testing, a tester triggers a failure that was caused by a defect. If we're just reviewing documents or code without running anything, that's static testing. The tester or a tool directly finds the defect.
So the tester is like the forensic expert, or maybe the person who runs the experiment that exposes the vulnerability.
Exactly. But, and this is critical, that's where the tester's job ends. Debugging is the repair activity that comes next. It's typically done by the developer.
Right, they have to find the root cause.
Find the root cause, analyze the defect, and then, code the fix to eliminate it. This is usually followed by the tester running confirmation tests, but that core distinction is clear. Testing is about measuring and detecting quality problems. Debugging is about fixing them.
This focus on early detection, it leads us directly to the 7 principles of testing. We can't cover all 7, but let's hit the 2 that fundamentally shape this whole discussion of the SDLC. Let's start with principle 3, which is really the core business argument.
Principle 3 is simple and powerful. Early testing saves time and money. This is the foundational financial argument for quality engineering. It's why we do all this.
So defects found early, say, when you're just reviewing the requirements, they don't propagate.
They don't propagate downstream into the design and then into the code and then into the test scripts and the documentation and the database schema.
And when they do propagate, what happens then?
The cost just explodes. I mean, the studies on this are universal. The cost multiplier is staggering. Fixing a simple ambiguity in a requirement during that initial review might cost, what, $10 in time and effort?
Okay.
If that same ambiguity is only discovered during system testing, just before release, the cost can jump to $1,000.
Wow.
And if the defect actually reaches the customer in production, the cost of the fix, the mitigation, the communication, potential legal exposure, you could be looking at $10,000 or more.
So that's a 100x to 1,000x cost multiplier.
It is. And that is the core, non-negotiable insight of Principle 3. It's the entire justification for the shift left philosophy.
That really puts the stakes into perspective. Okay, now Principle 6, which justifies why we even need to do this deep dive on SDLC integration.
Right. Testing is context dependent. This is essential because it just blows up the idea of a universal, canned test plan. You can't just copy and paste.
So you can't apply the same strategy to a high-risk medical device that you would to, say, a mobile game.
Exactly. You can't apply the same strategy to a system built using a sequential V model as you apply to a low-risk, fast-paced mobile app built with Agile Scrum. The test strategy, the choice of techniques, the extent of automation, the level of documentation, it all has to adapt based on the business domain, the risks, the regulations, the architecture, and most importantly, the software development lifecycle model being used.
And quickly, let's touch on that important cautionary tale, the absence of defects fallacy. That's Principle 7. If I, as a tester, achieve 100% test coverage against the specs, and I find and fix every single defect, why could the system still fail?
Because you might have failed the validation step.
Back to validation.
Always. The fallacy is believing that just because you verified the system against the specified requirements, it will succeed. The specifications themselves might be incomplete or wrong or just outdated. The system might not meet the actual needs and expectations of the user. Or it might simply be inferior to the competition.
As verification is necessary, but it's not enough.
It's not sufficient. We have to focus on validation and real-world utility.
Okay, finally, before we move on, let's frame the test process itself. The syllabus lists this common flow: planning, monitoring, analysis, design, implementation, execution, completion. But this is never followed rigidly, is it?
Oh, never. The general activities are constant, but the implementation is highly contextual. The strategy you choose, the level of detail in your documentation, the specific techniques you use, the degree of test automation, all of this is determined by those context factors we mentioned.
The skills of the team, criticality of the system, the SDLC model.
Exactly. The real art of test management is tailoring this generic process to the project's specific constraints.
That customization, that tailoring, brings us squarely into Chapter 2. How do we synchronize our testing strategy with the development model? The testing approach can't, and it really shouldn't, exist in a vacuum, separate from the process that's creating the software.
Indeed. The SDLC model, that abstract high-level blueprint for the project, is the single greatest determinant of the testing strategy. It really is. The choice of model dictates when test activities happen, the volume of test documentation, the need for automation, and even the roles and responsibilities of the team.
Okay, let's break down that impact, starting with the older, more formalized approach. Sequential models like waterfall or the classic V model.
All right. Sequential models are defined by these distinct chronological phases. One phase has to be completely done before the next one can even begin.
So testing participation here is governed by Principle 3, early testing.
It has to be. Testers get involved early in static testing activities. They're participating in requirement reviews, detailed analysis, and they're designing tests at the same time the design phase is happening.
So we're adhering to early testing, but the nature of the model forces a very specific constraint, doesn't it?
It does. A big one. Because executable code is only generated and integrated in the later phases, dynamic testing, actually running the software, starts much, much later in the lifecycle.
So you could have months of meticulously designed tests just sitting on a shelf.
You could, just sitting there, unused, because the build isn't stable or even available until month 7 or 8. And that delay, it inherently carries a higher product risk. Because if a fundamental architectural flaw is discovered that late...
The cost is massive. Back to Principle 3 again.
Exactly. Fixing it is a huge, costly undertaking.
And the contrast with iterative incremental models is it's dramatic. This includes things like the unified process, spiral models, or modern agile practices. What changes in the testing rhythm here?
The change is absolutely fundamental. The core assumption of these models is that each iteration delivers a working prototype or product increment.
A small working piece of the puzzle.
A working piece. So the testing process shifts entirely from that big phase gate approach, where you wait for one big delivery, to a continuous small cycle approach.
What does that constant incremental delivery demand from the testing team? I mean, that sounds intense.
It creates two massive simultaneous demands. First, because the product is released or at least demoed frequently, testing has to provide fast feedback on the quality of that latest increment. If your iteration is 2 weeks long, your testing and reporting cycle cannot take 3 weeks.
Right, makes sense.
Second, and this is the real technical challenge, extensive regression testing becomes completely non-negotiable. Every new feature you add, every change you make, risks breaking functionality that was built in a previous, successfully tested increment.
And this explains why agile methodologies, which are, the most common form of iterative development today, Scrum, Kanban, why they just can't survive without specific testing countermeasures.
That's exactly right. Agile development demands certain testing adaptations. Because you need to change things rapidly, Agile favors lightweight documentation. Testers can't spend weeks creating these exhaustive, detailed, specification-based test cases for every single user story.
So what's the critical response?
Extensive test automation, particularly for that massive, ever-growing regression suite. This is what makes the testing process repeatable, reliable, and fast enough to actually fit inside a short sprint cycle.
So if the automated regression suite is the shield, protecting what already works, what happens to manual testing in an agile world?
Manual testing becomes more focused. The source notes that it heavily relies on experience-based techniques. Since you don't always have exhaustive upfront documentation to derive spec-based tests from, testers have to rely on their skills, their intuition, their knowledge of common failure modes.
So things like exploratory testing.
Exactly. Designing and executing tests at the same time. Using your brain to find defects and risks that the automated suite or the written specifications may have completely missed.
This whole discussion really highlights a set of universal good practices that shouldn't depend on the SDLC model. I mean, these are things we should see in Waterfall, Scrum, and DevOps.
They are the pillars of integrated quality assurance, yes.
So let's list them. What are these non-negotiables?
Okay, first, the most philosophical one. Every development activity requires a corresponding test activity. If you're designing the database schema, there has to be a test activity to review that schema for quality and correctness. Testing is interwoven, not bolted on at the end.
Number 2 is about efficiency.
Right. Different test levels must have specific and different test objectives. We'll get into the 5 levels later, but component testing has different goals than system testing. You have to make sure you're not wasting time repeating the same check at multiple levels.
And third, we're reinforcing Principle 3 again.
Always. Test analysis and design must begin during the corresponding development phase. If the developers are gathering requirements for a new feature, the testers should immediately start their test analysis and design for that feature. It's the organizational commitment to early testing.
And finally, integrating the human review process.
Testers must be involved early in reviewing work products as soon as drafts are available. This means requirements, documents, architecture diagrams, design specs. This early static testing is the most cost-effective way to find defects, and it explicitly supports the shift-left movement.
Okay, let's talk about that. The mantra of modern quality, shift left. We know the principle find defects when they're cheapest to fix, but what does shift left actually look like in practice, organizationally and technically?
Shift left is the explicit, strategic approach of performing quality activities. Test design, static testing, reviews, environment setup earlier in the SDLC timeline.
So it's not just reviewing a document.
No, not at all. In practice, this means moving activities that were traditionally done in the late stages, like performance testing, into the early stages, often using things like mock services or prototypes.
So we're proactively building test environments, mocking out complex external dependencies, and designing the structure of our regression suite before the first line of code for a new feature is even written?
That's absolutely right. And the biggest component of shift left that doesn't require any executable code is static testing.
Right, the non-execution phase.
Using code analyzers, design reviews, formal inspections, all to find defects in the work products themselves. The value proposition is simple. You prevent the defect from ever even entering the codebase in the first place.
And while this takes more upfront effort,
It does. It requires extra effort, training, and maybe cost earlier in the process. But the syllabus confirms this is strategically necessary because it drastically saves effort and cost later by stopping that defect propagation we talked about.
what's the biggest barrier to adopting shift left? It seems like a total no-brainer given the 100x cost savings.
It's almost always organizational inertia and culture. It requires management to allocate resources to activities like requirements reviews and building test environments that don't immediately produce visible code output.
Right, it's not a shiny new feature.
Exactly. Convincing stakeholders that investing significant time on the left will reduce firefighting on the right is the main cultural challenge.
Building on that early engagement, modern development often uses testing to actually drive development, not just audit it. This is the whole idea of test-first approaches.
Yes, and all test-first approaches share the same mandate. The tests are defined and often written before the corresponding code exists. They guide the development.
So let's break down the three crucial types. First up, test-driven development, or TDD.
TDD. This is primarily an engineering practice for developers working on isolated components. The cycle is very strict and iterative. First, you write a small, automated component test case for a piece of functionality you want. And this test will fail initially because the code doesn't exist.
Okay, red.
Red. Then, you write the absolute minimum code necessary to make that test pass.
Green.
Green. And third, you refactor. You clean up the code and the tests to improve the quality, all while making sure all the tests still pass.
So TDD ensures developers only write code that is demonstrably necessary. It makes the code cleaner, less bloated, and the tests themselves become living documentation.
That's the key technical benefit. Now, moving up to the business layer, we have behavior-driven development, or BDD. This is all about collaboration and communication.
Right. BDD expresses the application behavior using test cases written in simple, natural language that everyone can understand.
And this is usually structured in that classic given, when, then format, right?
Precisely. Let's use a concrete example. Instead of a technical test case that says, assert user.balance is greater than withdrawal.amount, a BDD specification reads very differently.
How so?
It would say, given the customer has a balance of $500 in their checking account, when the customer attempts to withdraw $400, then the withdrawal is successful and the account balance is $100.
That language is immediately accessible to the product owner, the business analyst, the quality engineer. Everyone's on the same page.
It bridges that gap. And these natural language tests are then automatically translated into executable automated tests. So it guarantees that the tests reflect the user's perspective and that the team is building the functionality the business actually needs. It enforces validation early on.
And finally, there's acceptance test-driven development, or ATDD. How does this one differ from TDD and BDD?
ATDD is highly collaborative, and it operates at a slightly higher level than TDD. It focuses on deriving tests directly from the acceptance criteria for a user story or a feature.
So this collaboration involving the customer or product owner, the developers, and the testers happens early during the system design phase.
Exactly. By defining the acceptance tests before the application is built, the entire team knows precisely what criteria define done or complete. ensuring alignment and building the correct product from the very start.
All these test-first methodologies, they clearly demand continuous integration and rapid feedback, which is basically the definition of the DevOps philosophy.
It is. Let's detail how this cultural shift impacts the testing role.
DevOps is, at its heart, an organizational and cultural approach. It's designed to break down those traditional silos between development, which includes testing, and operations. The goal is one unified team with shared goals, shared responsibility, and extreme automation to manage the pipeline.
And what technical pieces enable this?
It's the continuous loop of continuous integration, CI, and continuous delivery or deployment, CD. And from a testing perspective, the CI process itself is a massive shift-left enabler. Well, developers have to frequently merge their code into the shared repository, and they are required to submit high-quality code that is already accompanied by their component tests, static analysis results, and possibly even proof of code coverage.
So the developer can't just throw code over the wall anymore. They have to prove its quality at the point of submission.
Correct. The automated CI/CD tools then take over. They establish stable, repeatable test environments on demand, and they orchestrate the entire automated test suite. This provides those fast feedback loops. If the build breaks or the regression suite fails, the developer knows within minutes.
Not days.
Not days. This massive investment in scaled automation minimizes regression risk, allowing the team to push code frequently without that constant fear of breaking the existing system.
That scaled automated regression testing suite is the backbone, but how do teams prevent that suite from becoming so massive that executing and maintaining it takes longer than the sprint itself? What's the practical trade-off there?
That is the single largest challenge in DevOps. It's the maintenance burden of the automation framework. If your automation is brittle, hard to update, and fails all the time because of environmental shifts or minor UI changes, your team will spend more time fixing tests than writing new features.
So what's the solution?
The trade-off requires ruthless discipline in test design. You have to focus the automation on high-risk, high-return tests. That's risk-based testing. You have to continuously refactor the automation code just like it was production code. And you have to constantly prune low-value or redundant tests. The human cost of maintaining a poor automation framework often outweighs the speed benefits.
Which brings us to the reality check on DevOps implementation. Despite the power of automation, what are the organizational and technical risks we have to watch out for?
The risks are significant. First, there's just the sheer effort required to define and establish the entire delivery pipeline in its complex toolchain. Second, introducing and maintaining the necessary CI/CD and automation tools demands specialized skill sets and budget. It's a major multi-year undertaking.
And the third risk?
The third is the risk of unrealistic expectations. The belief that automation is a silver bullet that will solve all your quality problems. But critically, the syllabus reminds us, manual testing, especially from the user's perspective and for exploratory activities, is still needed.
Right. Automation handles repeatability. Human testers handle critical thinking, context, and validation.
Precisely. And as we close the loop on this whole process, we have to mention the formal mechanism for improving it. Retrospectives.
So how do retrospectives formalize that continuous process improvement?
Retrospectives are mandatory meetings held at the end of a project, a release, or an iteration. They are cross-functional, so you have testers, developers, product owners, architects, everyone's in the room.
And it's not about assigning blame.
No, it's about analyzing the process. The team discusses what happened, what worked, what failed. Then they discuss why it happened. Root cause analysis on process flaws, like slow environment delivery or ambiguous requirements. And most importantly, they discuss how to improve the process and team dynamics for the next cycle. This ensures that the pain points identified during testing feed back into documented changes in the SDLC itself.
We've established when we test in the SDLC timeline and how we embed quality with shift left and DevOps. So now let's transition to where we apply these activities within the system structure, the test levels.
Test levels provide a structural hierarchy. They're organized groups of test activities, and each one corresponds to a specific development phase. You start from the smallest code unit, and you progress all the way up to a complex system that's interacting with external partners.
And each level is defined by 4 distinct attributes.
That's right. The test object, well, what exactly are we testing? The test objectives, why are we testing it? The test basis, what documentation defines correctness? And finally, the responsibilities, who actually performs the testing.
Okay, let's start at the very bottom, the smallest test object.
That would be component testing, which is universally known as unit testing. The focus here is on testing individual software components, modules, or program units in isolation.
In isolation. So because they're isolated, they usually require some specific technical aids, right? Like mock objects or stubs.
Exactly. You need things like mock objects, stubs, or test harnesses to simulate the environment or the surrounding components that aren't available yet. And this testing is typically performed by the developers themselves in their own development environment.
Okay, moving up a notch, we connect those isolated components.
And that's component integration testing. The focus here shifts from the internal workings of the component to the interfaces and interactions between components.
So we're checking if the different pieces of code, maybe written by different people, talk to each other correctly.
Correct. Are they passing data accurately? Are they calling functions in the right sequence? The success of this level heavily depends on the chosen integration strategy. Are you building the system bottom-up, top-down, or, the risky Big Bang integration?
That bottom-up versus top-down approach is actually a crucial decision for risk. With a bottom-up approach, you prioritize testing the lowest-level modules first, using drivers to call them, but the full system isn't visible until the end.
Exactly. And top-down prioritizes the user interface and high-level control flow first, using stubs to simulate the missing low-level components. So the integration strategy directly defines the test strategy for this level. And poor integration testing is a major source of really complex defects.
Once all the internal pieces are talking, we have a functional system, we can move to system testing.
Right. System testing checks the overall system behavior and capabilities. The test object is the entire integrated system or product. And the objectives here are really comprehensive, testing end-to-end functional tasks from the user's perspective, as well as critical non-functional characteristics like performance, reliability, and security, all on the complete package.
And this is often done by an independent test team.
Often, yes. Focusing on the system specifications, you need to verify that the whole is actually greater than the sum of its parts.
Now, for the distinction that often trips people up, system testing versus system integration testing.
It's a key distinction. System testing checks if our system works internally and meets its specifications. System integration testing is necessary when our system needs to talk to the outside world. The focus is on the interfaces between the system under test and external services, other applications, or the operating environment.
Can you use that car analogy to really drive this home for us?
Certainly. Think of building a modern car. Component integration testing would be checking that the engine management system component correctly communicates with the transmission control unit component via the internal wiring harnesses and APIs. That's all internal communication.
Okay.
System testing checks if the entire car engine brakes, steering accelerates when you press the pedal, and stops when you press the brake, meeting the overall car specifications.
And system integration testing.
That checks if the car's navigational system can successfully communicate with the external satellite network for GPS data, or if the car's remote diagnostic system can exchange data with the manufacturer's central server over the cell network. You're testing the communication and data integrity between distinct independent systems.
And that requires environments that closely mimic the live operational setting.
It has to.
Okay, finally, the highest level focus purely on the customer, acceptance testing.
Acceptance testing is the final gate. It's focused purely on validation and readiness for deployment. The objective is confirming the system fulfills the user's actual business needs and criteria. This is ideally performed by the intended users or customers.
And the syllabus defines various forms of this.
It does. There's user acceptance testing, UAT, by business users, operational acceptance testing, which checks procedures like backup and recovery, contractual or regulatory acceptance testing for legal compliance, and of course alpha and beta testing, which involve testing by potential users outside the developing organization.
The moment acceptance testing is done, the change cycle begins again. Someone finds a bug, a developer fixes it. This triggers the two essential maintenance practices, confirmation and regression testing.
They're completely inseparable. When a defect is fixed, the very first step is confirmation testing, often just called retesting. You simply rerun the original failed test, and maybe a few related ones, to confirm that the reported defect has been successfully eliminated.
The failure no longer occurs.
Right. Then comes the insurance policy, the practice that really forces the need for automation in modern cycles, regression testing.
So regression testing confirms that the change, the fix, or the new feature did not introduce unintended side effects.
Regressions.
Exactly. Adverse side effects elsewhere in the system, its components, or the environment. A small fix in the payment module might accidentally introduce a major flaw in the invoicing module. Regression testing minimizes that risk. And because code is changing constantly and that regression suite is always growing, automating this process is paramount.
But we can't run the entire suite every time. That would take forever. We have to be smart about what we run, which necessitates impact analysis.
Impact analysis is the essential scoping exercise. Before you run any regression test, you have to analyze the change itself to identify which specific parts of the software and potentially which connected external systems could possibly be affected. That analysis determines the prioritized subset of regression tests you have to run. It ensures efficiency, and it links this entire process back to risk management. Okay, we've covered the structural hierarchy with the levels. Now let's look at the functional hierarchy. The specific quality characteristics we check for, the test types. And these can apply at any level, but the focus shifts, right?
It does. A test type evaluates a specific quality characteristic. We generally categorize them starting with the most basic, functional testing. This focuses on what the system does.
Is it complete? Is it correct? Is it appropriate?
Exactly. Is all the required functionality present? Does it produce the right results? Is the function designed to solve the business problem? These are all derived directly from the specified functions.
Then we shift to the how well aspect, the part that defines user experience, stability, and market competitiveness. Non-functional testing.
Right. Non-functional testing evaluates every other attribute, often derived from the ISO AE 25010 standard for system quality. This is testing how well the system behaves, and crucially, these defects pose the highest risk of being discovered late and causing a major project failure.
Okay, let's detail those ISO characteristics. Explain why they're so high risk if you neglect them.
Okay, so we look at 1. Performance efficiency. This is testing speed, responsiveness, resource use, the risk of late discovery. A system might work perfectly functionally, but if the response time under load is 5 seconds instead of half a second, the business is going to suffer crippling customer churn.
Makes sense. Number 2.
Compatibility. Does it work with the intended operating systems, browsers, hardware? The risk here is finding out your web application only works on Firefox after you've deployed it, which means you've just blocked a huge segment of your market.
Okay. Usability.
Usability or interaction capability. How easy is the system to learn and use? Late discovery means users struggle, training costs skyrocket, and the system is abandoned, even if it's technically perfect. Then there's reliability testing, maturity, fault tolerance, recoverability. Late discovery here means the system frequently crashes or loses data, which is a severe operational risk.
And the big one, security.
Security, confidentiality, integrity, non-repudiation. The risk of late discovery here is catastrophic. Data breaches, loss of customer trust, major financial and legal penalties. And then we have maintainability, how easy it is to fix or enhance the system, and portability, the ability to adapt to different environments. Late discovery on those means high maintenance costs and getting locked into a specific vendor.
That list really shows the complexity of quality. And what's the organizational key to testing these things? We can't just wait until the end.
The key, and this reinforces shift left, is that non-functional testing has to start early. We can check security compliance via static analysis of code during component design. And the crucial link is that many non-functional tests are derived from existing functional tests just by adding in constraints.
So you don't need new steps.
You don't. You just run the functional test while you're measuring the response time or while you're monitoring memory consumption. And just like that, you've turned a functional check into a performance check.
Our final major categorization distinguishes test types based on their source of information. Black box versus white box techniques.
These techniques define how we construct the test cases. So, black box testing, or specification-based testing, derives tests purely from external documentation requirements, user stories, interface specs, things that are not related to the internal structure of the code.
So you're treating the system like a black box. You only care about the inputs and outputs against the required behavior.
Exactly. The main objective is verifying that external behavior against the specification. And the techniques here include things like equivalence partitioning, boundary value analysis testing, the limits of ranges decision table testing, and state transition testing.
And a huge benefit is that if the internal implementation is completely changed,
The black box tests often remain 100% useful because the required external behavior is unchanged.
in contrast, white box testing, or structure-based, requires us to look inside the box.
Yes, this derives tests from the system's internal structure, the code, the architecture, the data flows. This is often performed by developers or expert testers. The primary objective is to cover the underlying structure to an acceptable level.
And this level is measured using coverage metrics like statement coverage or branch coverage.
That's right. Statement coverage ensures every line of code is executed at least once. Brand coverage ensures every decision point, like an if statement, is tested for both the true and the false outcomes. White box testing ensures that the implementation logic itself is sound and fully exercised.
So black box confirms you built the right thing. White box confirms you built the thing right internally. And you need both for holistic quality.
You do.
Moving into test management, we've got all these levels, all these types, all these methodologies. How does a manager or a team lead prioritize their effort? I mean, we can't test everything everywhere. That's where risk-based testing becomes central.
Risk is the prioritization engine. It has to be. Risk-based testing simply means that test activities are selected, scoped, and prioritized based on analyzing risks. And every risk is characterized by two factors: risk likelihood, the probability of it happening, and risk impact, the severity of the consequences.
And the overall risk level is the product of those two, likelihood times impact.
Exactly.
So let's get practical here. How do teams actually measure likelihood and impact?
Well, teams often use a quantitative scale, maybe 1 to 5. Likelihood might be a 5 if a component was rushed and it's really complex, but it might be a 1 if it's a simple, well-tested library. Impact might be a 5 if failure leads to a complete system shutdown or major financial loss, but it's a 1 if the failure is just a minor cosmetic issue.
So a risk with a likelihood of 5 and an impact of 4 gives a risk level score of 20. That's a high-risk area demanding maximum attention.
It is, and we deal with two distinct categories of risks in testing. There are project risks, which relate to the management and control of the project itself. They threaten the success of the project. These like inaccurate time estimates, budget shortfalls, staff turnover, insufficient skills, or poor tool support. These are management problems that can derail the whole testing timeline.
And then there are product risks, which are what the testing team is fundamentally designed to address.
Right. Product risks relate to the quality of the application itself. They threaten the quality of the final product. These are your bugs, your security flaws, performance bottlenecks, poor usability. When a manager scopes the testing effort, the product risk analysis is the driver.
So if we identify a high-risk area, say that 20 on our scale, how does that translate into specific actionable test measures? What do we actually do differently?
The risk level dictates the thoroughness and scope. For that score of 20, a manager has to implement really stringent measures, potentially doubling or tripling the effort compared to a low-risk component.
So this means assigning your best testers.
It means selecting only the most experienced or specialized testers. It means increasing the level of test independence, maybe using a dedicated, separate test team rather than the developer testing their own code.
And you do more static testing first.
Rigorous formal reviews and static analysis first, yes. You'd apply specific, intensive white box or black box techniques, like using all 3 boundary values instead of just 2. You'd aim for higher coverage targets, like mandatory 100% branch coverage for that specific module. And you'd perform frequent dynamic testing and continuous automated regression testing on that area.
So the effort is focused precisely where the consequences of failure are highest. This necessity for frequent focused testing drives the reliance on tools, especially in the modern SDLC. What role do tools play across the lifecycle?
Tools are essential because they automate the repetitive, complex, or time-consuming parts of testing, enabling the speed that iterative development demands. We use tools across every single phase. Test management tools track requirements, traceability, manage defect reporting, and handle configuration control. Static testing tools perform code analysis and check adherence to coding standards. Test design tools can generate test cases or complex test data automatically.
And then you have the tools that really enable DevOps.
Yes, the test execution and coverage tools that run those automated tests and measure code coverage, providing objective data. Non-functional testing tools that can simulate massive load or monitor security vulnerabilities in real time. And finally, specialized DevOps tools that manage the entire CI/CD pipeline, automating builds, environment provisioning, and deployment.
The ultimate goal is often test automation. We've talked about the benefits, time savings, consistency, fast feedback, but let's just reiterate the organizational risks that have to be managed beyond just the maintenance effort.
Risk management absolutely has to account for these pitfalls. The most common organizational risk is, again, unrealistic expectations. Management believing automation will solve staffing shortages or eliminate manual testing entirely.
Which it never does.
Never. Second is the cost and vendor risk. Automation frameworks require high initial effort and a continuous budget for maintenance and training. You risk choosing the wrong, overly complex tool or becoming dependent on a vendor whose support might be withdrawn, or relying on an open-source tool that might be abandoned. Over-reliance can also lead to tunnel vision, focusing only on what is easy to automate rather than what is important to test.
So automation is a strategic business investment, not just a technical implementation.
Absolutely. It needs clear objectives, dedicated resources, and critical human oversight. It should free up the expert human testers to focus on the high-risk, experience-based testing that automation simply cannot handle.
Finally, let's tie this back to the continuous improvement loop. Retrospectives are a core activity in the test completion phase. What is the overarching purpose of all test completion activities?
Test completion occurs at formal milestones: the end of a project, the end of a major release, or the end of an iteration. And the goal is twofold: operational closure and process improvement.
Okay, what does operational closure involve?
Operational closure involves tracking any unresolved defects, turning them into change requests or backlog items for the next cycle, and archiving useful testware, the test cases, the test data, the reports, so they can be easily reused for future maintenance or regression testing.
And the improvement side is the retrospective.
Yes. The retrospective is the formal mechanism for learning lessons. By gathering that cross-functional team, you ensure the pain points that were experienced, whether they were poor requirements, unstable environments, or insufficient automation, lead to positive documented changes in how quality is assured going forward. It ensures that the process that created the product is reviewed, not just the product itself. This closes the quality loop and drives true continuous improvement. Hashtag outro. What defines success in quality engineering, as you've seen across all these chapters, is adaptability. Testing success hinges entirely on aligning the right activities, the right test levels, the right test types, and the right degree of automation with the specific constraints and, critically, the lifecycle model of the project. Good testing is adaptive, it's context-dependent, and it's constantly refined.
And that is the essential insight we wanted to deliver. Your foundational knowledge of testing is only useful if you understand how the SDLC model dictates its application. The transition to iterative and continuous models, from sequential waterfalls to DevOps, it drives the necessity of early testing, of shift left, and it mandates high levels of automation to manage the speed and risk of constant change.
And as we reflect on that continuous movement, where CI/CD and automation push defect detection earlier and earlier, reducing the scope of traditional testing phases, we have a provocative thought for you, the learner, to consider.
Okay.
If continuous integration requires developers to submit high-quality code with component tests, and static analysis tools perform initial verification on code structure, what is the fate of the classic dedicated test level? Will component testing eventually dissolve entirely into the developer's definition of coding and build automation, leaving the dedicated testing role to focus purely on complex system integration testing, external risk management, and the high-value subjective art of user-facing validation?
The role is changing fast.
It is. And that is a crucial question to explore as you apply this knowledge.
A lot to chew on for your next project. Thanks for diving deep with us. We'll see you next time.